The magnitude of a vector is kind of like the size of the vector. When we were drawing our directed line segments earlier, the magnitude was represented by the length. Another word that you may hear occasionally for magnitude is norm, the norm of a vector. So if we've got, we're going to do this two ways. If we've got a vector, or excuse me, a point P at x1, y1, and a point Q at x2, y2, the way that we write magnitude is with absolute value bars. So anytime you see absolute value bars around a vector, they're asking for just the magnitude of the vector. So no matter where P and Q are located, we saw earlier that you can connect P and Q with just one horizontal movement and one vertical movement to get from P to Q. But the actual vector PQ goes directly there. So what we've created here is a right triangle where this horizontal component and the vertical component are like sides of the legs of a right triangle, but the magnitude of our vector is really the hypotenuse. So we could solve this just with a Pythagorean theorem. So if we've got coordinates here, the way that I figure out this horizontal distance is I find the difference in my x coordinates. So this side right here is x2 minus x1. And the way I find the vertical difference between them is subtract the y coordinates, y2 minus y1. And that will give us the lengths of those two legs. And then the Pythagorean theorem says a hypotenuse is the square root of the sum of the square of your legs. So we can go directly from the terminal initial point to a magnitude formula, or we can also use components. Because remember, this distance right here, we might also see it written as just v1, the first component of our vector. And then the horizontal or the vertical piece is v2. So if I already knew x2 minus x1 was my first component, then this entire x2 minus x1 in the formula could be replaced just with v1. And y2 minus y1 is just my second component, so that entire second term under my square root can be replaced with v2. So in component form, we could also calculate it as the square root of v1 squared plus v2 squared, where v are our components. Component form is the absolute easiest way to calculate any sort of vector operations. So if we want to add two vectors together, let's say we've got vector v has components v1 and v2, and vector w has components w1 and w2, we can create a new vector by adding them together. We can figure out what v plus w is just by adding their corresponding components. Because both v1 and w1 are horizontal components, since they point in the same direction, we can add them together. And then v2 and w2 are both vertical components, and since they point in the same direction, I can add them together. And we get a new vector that's still in component form that has components v1 plus w1, and we're adding here because we were told to add the two vectors together. And the second component is v2 plus w2. For scalar multiplication, we're taking a vector in component form, v1, v2, and we're just multiplying through by some scalar c. So c is going to be just a number. Remember, scalar quantity has magnitude but no direction. So whatever the value of c is, we just distribute it to both of the components to get the scalar multiple. And then if c was a negative, just as an example, if I wanted to find negative v, I would distribute a negative into my components, and I would get negative v1, negative v2, and that we need to use in order to do subtraction. Vector v minus vector w is the exact same thing as vector v plus the negative of vector w, and that's going to help us in a few minutes when we try to draw these. Since we're already in component form, these calculations are very easy from component form. You just combine your components with whatever operation they tell you to. So we would do v1 minus w1, v2 minus w2. So algebraically, these vector operations, as long as we're in component form, can be done just component-wise. For addition, you just add like components. For subtraction, you subtract like components. For scalar multiple, you distribute to both components. And we'll do some examples in just a minute once we talk about what these operations look like geometrically. So for vector addition, there are two different techniques you can use. One of them is called the parallelogram method. And with the parallelogram method, you can only use two vectors at a time. We take our two vectors and we put them in standard position, and then we use them to create a parallelogram. The sum of our two vectors is the diagonal of that parallelogram, the diagonal that's in standard position. So remember, standard position is when both vectors have initial point at the origin. So let's say that's vector v, and then here's vector w. I have both of them drawn in standard position, and I am going to consider these two vectors to be the non-parallel sides of a parallelogram. So we need to try to draw what that parallelogram looks like as best we can. So we finish off the other two sides. And then the sum is the diagonal that's also in standard position. So that vector would be v plus w. So parallelogram method is nice because if our vectors are in component form, that means they are standard position vectors. So it's very easy to draw our two initial vectors in standard position because that's how they're going to be given to us. What can be kind of tricky is drawing the parallelogram accurately. You just need to remember that the side opposite v should be parallel to v, the side opposite w should be parallel to w. But you do have another option if finishing out that parallelogram is a bit tricky. The other option is the polygon method. And with the polygon method, what we're going to do is we're just going to create a chain of vectors. And the nice thing about the polygon method is we're not stuck doing this just between two vectors. We can use an unlimited number of vectors with the polygon method. And we're going to create a chain where I place the initial point of one vector at the terminal point of the previous vector. So I'm going to draw my first vector in standard position, and where that vector ends is where I'm going to start my next vector. So I'm going to try to draw these the same as I did above. So there's vector v. Instead of drawing w in standard position, I'm going to draw w where v ended. So I'm making a chain, kind of a head to tail chain. Where v ends, w starts. And if I have a third vector where w ends, my next vector could start. The sum of the vectors is when we connect the very beginning of the chain to the very ending of the chain. And since I only used 2 here, it would just be v plus w. And if you look at the picture above, some of our work is different, but v plus w looks exactly the same. So we could do it either way. We'll still get the same exact answer. Just whatever I guess makes more sense to you. For scalar multiplication, since all we said we were going to do algebraically was distribute the value to both vectors, that's going to change our magnitude. It could make our vector much longer or much shorter depending on the scalar, but it's not going to change the direction of our vector. It's still going to point in the exact same direction as long as that scalar is positive. It will make it turn exactly 180 degrees and point in the opposite direction if it's negative. So if this is vector v, and I'm going to give it some components just so you can see exactly what happens here. If vector v has components 2, 1, then 2v, we're going to distribute 2 to both of those, is going to be 4, 2. And 2, 1 and 4, 2 are in a perfect alignment with each other. Since we multiplied by 2, I've got a vector pointing in the exact same direction, but now it's twice as long. We could also draw negative v. I'm going to draw this one on a different graph. So that's vector v, which has components 2, 1. Negative v would have components negative 2, negative 1, which essentially turns it 180 degrees and makes it point in the exact opposite direction. And we're going to use that to help us figure out how exactly to draw subtraction. So we need to think of subtraction as adding the opposite. And the reason we need to do that is because the parallelogram and the polygon method we just talked about are specifically techniques for adding vectors. So there's not a nice, easy subtraction technique. Instead, we're just going to change it into add the opposite. That way we can just use polygon or parallelogram method again. So let's say that's vector u, and there's vector v, and we want to figure out u minus v. The first thing we need to do is draw negative v, and negative v would be the exact same length but pointing in the exact opposite direction. So there's our negative v. And then now I can do parallelogram method between u and negative v. So that kind of looks like a parallelogram. So u minus v, or u plus negative v, is the standard position diagonal. So it's a combination of the concepts of a negative scalar and our one of our methods for addition, either parallelogram or polygon. It's probably much more natural to do parallelogram method if you're just working with 2 vectors, because you can draw your vectors in standard position, which is how they're going to be given to you. But if you've got 3 or 4 vectors that you need to add together, polygon method might work better. So we're going to look at a quick example. We have got vector v, which has components 5, 2, and vector w, which has components -2, 1. The first thing we're going to do is we are going to calculate the magnitude of vector v. So remember, magnitude is the length or the size of our vector, and we can think of those components as the legs of a right triangle. What we're trying to calculate is the hypotenuse. So the magnitude of vector v is 5 squared plus 2 squared, all under a square root, which is going to be 25 plus 4, square root of 29. 29 is not a perfect square, and most of the time here we want exact answers, so we leave that as square root 29. Next, we are going to algebraically and geometrically calculate v plus w. So algebraically, all we have to do is add corresponding components. So 5 plus -2 is 3, 2 plus 1 is 3. If we wanted to do this geometrically, I'm going to draw both of my vectors in standard position. So there's 5, 2. And our second vector is -2, 1. And if we make a parallelogram out of them as best we can, remember we want those opposite sides parallel. Our sum is the diagonal that's in standard position. And it looks like that diagonal has terminal point 3, 3, exactly what we were able to figure out algebraically. So we just said that vector v had components 5, 2. And we are going to figure out what 2v is, and what -v is, and what 1/3 v is. Algebraically, these are very easy. All we have to do is distribute those scalars into both of our components. So for 2v, I just have to multiply both 5 and 2 by my scalar of 2. So we get 10, 4. -v means we're just going to distribute a -1. So -5, -2. And 1/3 of v means I'm going to distribute a scalar of 1/3 and multiply. So that's going to give us 5/3, 2/3. And we can draw this. So there's approximately 5, 2. Here is 10, 4. And besides my terrible art skills, they should be right in line with each other. The only difference now is that 2v is exactly double the length of the original v. And then -v is -5, 2. -5, -2. So that's going to take our v and just point it in the exact opposite direction. And then 1/3 of v is going to take our original v here and cut it down to 1/3 of the original length. So 5/3, this is going to be tricky. 5/3 is about 1 2/3. So it looks like we're right here. And that looks pretty good as almost exactly 1/3 of the length of the original v. Remember, scalar multiples don't change the direction, just the magnitude. Unless we're doing a negative, then it will flip at 180 degrees. All right, one more example really fast. We are going to try to figure out V minus W. So remember, V was 5, 2, and W was negative 2, 1. Algebraically, this is going to be pretty easy because we just have to calculate the V components minus the W components. So 5 minus negative 2 is really going to be 5 plus 2, which is 7. And then 2 minus 1 is 1. And hopefully when we draw this, it will match up with 7, 1. So there's our V at 5, 2. W is at negative 2, 1. But remember, to geometrically draw subtraction, we really want to add the opposite. Because addition, we can do polygon parallelogram method. So I need to figure out first what negative W is, and that's just distributing a negative to my two components. That's going to put me at 2, negative 1. So exact opposite direction. And then now I can do the parallelogram method between V and negative W. So we just do our best to make those sides parallel. And the answer is the diagonal that's in standard position. And if we did it nice and accurate, it should have a terminal point of 7, 1. Your geometric picture and your algebraic work should match up.